Here's a question about cutting a rectangular pane of glass into 3 parts. If you have ever gone to Western Europe, you'll see many of these stained glass windows, where you have a window and it's cut into many little pieces, and there are nice pictures inside. This is a window which only has a geometric picture inside. A rectangular window with sides of 16 and 30 is divided into 3 panes. Let's draw what this looks like. 16 and 30 looks maybe something like this. And I'm dividing it into 3 parts. And so the 3 parts have a diagonal which is drawn, together with a line segment that is perpendicular to the diagonal, with one endpoint at the center of the rectangle, and the other endpoint on the edge of the rectangle. Like this. What is the area of the smaller of the 2 triangles formed? So here what we see is that there are 2 different triangles here, and this is the area I'm interested in. And the sides that I have are 16 and 30. How to start a question like this is to first try to label as much as we know about the picture. So I'm going to draw another picture on the next screen, much larger. Let's start again with the big rectangle. And this time, let's draw this line like this. And from the very center, let's draw a line that's going up perpendicular. Okay. Remember that some of these are right angles. So, for example, this is a right angle. Let's label more things. I don't have very nice angles in this picture, so I'll only label the ones which are 90 degrees. I know some sides. This side here is 16. The other side is 30. Maybe I'll draw it on this side. Can I find anything else? Well, actually, I think I can find this one because I have a Pythagorean, I have a right triangle for which I can use the Pythagorean theorem. Let me go to the next screen just to calculate what that might be. If I have a right triangle, which is 16 and 30, and I want to know what the other side is, notice that these are both even numbers. It's always easier to think of this then as 2 times another one, which is 8 and 15. This is using a method which is called similar triangles. And a similar triangles are triangles for which the same angles are the same, the corresponding angles are the same, and then the sides all scale by the same amount. This is a very powerful technique in geometry. 815 is a very famous Pythagorean right triangle. If I want to know what is the length of this side, I need to know what is 8 squared, which is 64, plus 15 squared, which is 225, which when I add together gives me 982, 289, which happens to be 17 squared. And so I have one of these very nice 8, 15, 17 right triangles, which I chose the numbers for to introduce it to you. Now, over here, that means this is 2 times it, so this is 34. So let's go back to the picture. Now I know that that long diagonal is 34, so each of these is 17. Now, I said I want to label as much as I can about this picture. But the problem is that I don't know what these angles are. You would need to use a subject called trigonometry to do that, with sines and cosines and tangents. I don't want to do that because my numbers would get messy, and also because on the AMC10 you can't use a calculator. Instead, I want to label things that I know by just marking angles which are equal. So for example, whenever I have 2 parallel lines cut by this transversal, I know that these 2 angles are the same. That's for sure. Is there anything else that I know is the same? Well, let me use another color. I do know something else is the same. These 2 angles are also the same because of that fact that this is 2 parallel lines with a transversal. But if you look very closely, there's another place where this green angle appears. You see, because the green angle and the blue angle are complementary, they add up to 90. Over here, they also add up to 90. So actually, I have another similar triangle here. This triangle here which I'm now going to label in blue. This triangle here is also similar to the 8, 15, 17 triangle. Wait a second. This triangle is similar to 8, 15, 17. What are the sides? I'm going to use this dark red. I'll write quotation marks also. This should be the 8 side. This should be the 15 side. And this should be the 17 side. But it's actually 17. So actually what it means is that this triangle, which I'm trying to figure out, is a scale factor of the 8, 15, 17 triangle. My answer to this blue thing is that I take my regular 8, 15, 17 triangle, 8, 15, 17 triangle, and I scale it by 17 divided by 15, because that's how I make this side actually 17. Now, how hard is it to solve this? I need to know the area of this multiplied by the square of what I scale it by. So now I can finish. 8, 15, 17 area. 8, 15, 17 area is 1/2 base times height, which is 4 times 15, which is 60. And then what I do to finish is I take my 60, multiply by the square of the scale factor, 17 over 15. So it's 17 squared over 15 squared. Perhaps I actually shouldn't have already multiplied because I'm about to cancel a 15. But if I cancel it, then I get 17 squared, which is 289. I'll still have a 4 from the 60. Divided by, I'll have 115 left over underneath. This 15 has a 3 and a 5, neither of which go up there. So I just have to finish by calculating 289 times 4, which I'm going to do because that's a nice number that you might run across again in the future. Times 4, 4 times 9 is 36, 4 times 8 is 32, plus 3 is 35, 4 times 2 is 8, plus 11, 56. I said it's a number you'll see in the future because 4 times 17 squared is 34 squared. Just so that you know, this is actually 34 squared, and you might see that again. But to finish, the answer is just 1156 over 15. So that's it. Let me go back and review. The key insight in this problem was when you have a question, label what you know. Sometimes the angles you can't calculate. They're not always 30, 60, 90. But see if you can see any of the angles that are same as other ones. And this idea of similar triangles, which we used for the easy part of the Pythagorean theorem here, is actually able to do very powerful things over here as well.